So again, morning all. We are going to be doing the physics of a dry cell. Now it's a little bit of chemistry here, but you're just going to see how it works. So reading from our handout, I just increase the size of this wordings. So it's easy for everyone to see. All right, so a dry cell, reading from our screen, guys. The device we use to create electricity in our circuits, our toys, our handheld devices, etc. is called a dry cell. Why is it called a dry cell? A dry cell basically is a paste, some sort of paste, a chemical paste that creates electricity. Now, long ago, well, not even long ago, in some other cells, they used to use a liquid, like the batteries, and the car battery has liquid in it, it has acid in it. And so those are what we call lead acid batteries. They actually contain a liquid, but for the dry cells or the batteries we use commonly, your Energizer, Duracell, all the other bogus versions of Eveready and those weird ones we see coming up every day. Those are what we call dry cells. Why is it dry? Because it's essentially made of a dry material, ish. So let's look and see. A dry cell consists of an anode, which is a negative pole, a cathode, which is a positive pole, and materials that create electricity via chemical reaction. The dry cells we use, as in commonly used in all our devices, is called an alkaline battery. Why is it called an alkaline battery? Because it has an alkaline type material in it. All right, sorry about that. So here, let's just look and see, zooming in a wee bit. This is the basis of our alkaline battery. So we have a metal cap at the top, right? So your metal cap at the top is going to tell us where we have our positive. Where's my pen? Oh, let me just pause. So if you were to look at our dry cell, it has what on it? It has a center core. All right, this is our center core in the middle here. This is our center core that goes up to your metal cap. All right, so that's our center core. And we have at the top our positive pole. And around that center core is a liquid, not liquid, a paste made of manganese dioxide. And what happens, the manganese dioxide is going to have a reaction with the zinc case and a reaction with the carbon rod. And what happens, that little reaction creates electricity. So around, if you look here, your casing here, look at it properly, your casing is not actually touching the inside of your battery. So that's why the bottom of our casing is going to be our negative pole. So always the little piece with the cap, that little piece of cap is connected to your carbon rod. And that carbon rod is what is producing your, that's your positive pole. So that is why we have at the top of our battery, that little piece that sticks out. That is why we always connect that to the positive pole in our connections or any kind of battery connection. You also will see where they'll say to list it as positive. But even then, everybody here knows whenever we have a battery connected to put in our battery a battery holder, we are going to have one end with a little spring, right? And that little spring, okay, that's a really bogus looking spring. All right, that little spring, excuse me, will always be your negative pole connector, and the other side will be your positive pole. So anytime you're in doubt, always the little springy part. Why does the little springy part connect to your negative pole? If you look at the base of your battery, you're going to realize that there's a little indent in it. Anybody ever notice that?
Yes.
Yeah, right. So that little indent is why we have this spring, because the spring is going to come and fit very nicely into this piece here, so it doesn't really pop out that easy. So that's why if you Ever in doubt, the springy part is always your negative pole or connects to your negative pole, and the next side will be your positive. A little tip when you all are taking batteries out of a container, whatever, don't just try to pull it out. What you're gonna do, you're gonna press down, right, on the spring. So always press down on the spring, so you pull it towards the spring so that the spring compresses and you are able to lift your battery out cleanly. So please, guys, don't mash up our battery holders, don't mash up your equipment, right? Because to put back in that spring is a real big problem sometimes. So just remember, anytime you have to take out a battery, you push down your battery, you compress that spring, and then you can easily pop out your battery. So this is why they say to always use your things properly. Right? Always remember. My pen is not working. Okay then. All right, moving on. We'll figure out that afterwards. The pen's not working at all. Just now, guys. So let's read up how your dry cells work. Reading from our screen. Let's just get a little bit in closer. Dry cell batteries create electrical energy by converting chemical energy into electricity. And what happens here? We are going to have something where we have the movement of positive and negative charges. And what we do, we funnel our negative charges through our circuit. The exact means of doing so depends on the type of battery cell, the type of dry cell battery in question, but the materials used are generally zinc, carbon, or zinc and manganese dioxide. Most of your dry cells are like this. What you all have to do for exams, you have to be able to list or learn what your carbon rod, where your carbon rod is, because it could come for exams where they ask you to list on to label a dry cell. So all you're going to have to do is not draw it, they're going to ask you to label it. So you have to be able to identify your carbon rod. You have to be able to identify what is the paste inside. So you have to remember them. And you have to identify your zinc casing. All right, so that's what you have to be able to do for exams. All right, continue reading. The materials are placed within the electrolyte paste or within the battery. This electrolyte paste is the manganese dioxide. Really, they don't ask you to learn what the material is. It's not required for you all to learn it. I just usually tell the other class because they know the chemistry, they have to do it in chemistry. So reading, they react with each other through a chemical process in which the electrolyte or the carbon or the manganese dioxide reacts with the zinc, creating electricity. This is transmitted out of the circuit using the positive and negative electrodes. Battery leaks. Anybody here ever encountered a leak in battery?
Yes.
What does it do to if you have a leak in battery in your device or your component or whatever? What happens to it?
It will heat up.
It'll heat up, and then what else?
The cell is explode.
Right, it does what we call exploding. It doesn't actually explode. Well, I hope you all don't have batteries that explode, but anytime we say a battery starts to leak, we say that it has exploded. Right? Now, what happens there? Let's read and see why that happens. Alkaline batteries, now the batteries that we use are called alkaline batteries, are prone to leaking potassium dioxide or some other material within your battery. A caustic agent that can cause respiratory and eye and skin irritation. So guys, anytime you all encounter a leaking battery, when you have taken the battery out and you get that liquid on your hands, please go and wash it immediately. It may not feel like it's burning your skin, but if you get it to more sensitive parts of your body, like your eyes or your face or anything, you're going to be, it's not going to be a nice experience. Nothing terrible is going to happen to you. to say like you're going to get some sort of poison or whatnot, but it is an irritant and it's the type of oily-ish little kind of substance. So we do suggest you go and wash your hands ASAP quickly with some good soap and water. The soap and water is enough. You don't require alcohol or anything special. The risk of this can be reduced by not attempting to recharge disposable alkaline batteries. Now, we do have disposable rechargeable batteries. They are made slightly different when compared to a regular battery. So you cannot recharge a regular disposable alkaline battery, which is the batteries that we use or the dry cells we use in common practice. All right, we can say by not mixing different battery types in the same device. That's kind of hard to do, but you don't want to mix different types of batteries. Usually put you one type of battery in your stuff by replacing all of the batteries at the same time. Now, this is something we all do wrong a lot. We will see that a device is not working, especially like our remote that has two batteries. And we say, okay, one of the batteries is probably not working. Let's put in a new one. Whenever you're replacing batteries, you have to replace both of them. Okay, or how many ever you are using. By storing batteries in a dry place at room temperature. So usually you want to store your batteries in somewhere that is at room temperature, a little cooler than room temperature. So somewhere like in a drawer, a bottom drawer of somewhere, so that way it's cooler, right? If you have any drawers or something in around in your room, you realize the top drawer is usually a little warmer than the bottom drawer. So anytime you have to store batteries, you want to store it somewhere that is dark and really cool. It's not necessary to put them in the fridge, right? Really not necessary to do that. Continue reading. All batteries gradually self-discharge whether installed on a device or not. So that means they will start to lose some of the electricity over a while. If you look at all your dry cells, now it's usually well labeled on your D cell batteries, you're going to see an expiry date on them. That expiry date usually indicates that all the electrons and not electrons, all of the ions and whatnot will have depleted, right? Because that chemical reaction will keep on going. It keeps on going whether or not you're using the battery. It does takes a very long time to discharge or to, as you say, self-discharge here when it's sitting by itself. But batteries are not meant to last forever. They will self-discharge or they will burn out their chemicals, not burn out, but use out their chemicals over a certain amount of time. And dead batteries will eventually leak. When your battery dies, it will start to leak. So this is usually your number one cause, right? Well, we're going to see it a little later here. Let's read. Extremely high temperatures can also cause batteries to leak or rupture, such as in cars in summer. Well, here too, we can get, if you have really hot days, we can get a leaking battery. Batteries can leak. This is why I think we have far more battery replacements in the tropics than in temperate climates, as well as a decrease in the shelf life of batteries. The longer a battery sits in a cupboard or on a shelf, as they say, it is going to lose some of its charge and it's going to eventually die. And you don't want to use dead batteries because dead batteries do leak. The reason for the leaks is that as the batteries discharge, either through usage or gradual self-discharge, the chemistry of the cells change and some hydrogen gas is generated. This outgassing increases the pressure in the battery. As you all know, some batteries, you do start to see some batteries swelling, right? If you've ever noticed a battery starting to swell, please don't use it. You take it out immediately and dispose of it, all right? Because anytime your battery has started to swell, that means it's producing too much hydrogen gas and it's going to rupture eventually. All right, so reading again. Eventually, the excess pressure either ruptures the insulating seals at the end of the batteries. That's why you realize the top of the battery usually starts to leak, or the bottom of the battery starts to leak, or the outer canister, or both. In addition, as the battery ages, its steel outer canister may gradually corrode or rust, which can further contribute to the containment failure. I am sure you all have encountered a rusty battery. Anybody ever encountered a rusty battery?
Yes, miss.
Yeah? If you all see a rusty battery or a battery where the poles are green don't even risk putting it into any sort of device, right?
Green
Any,
mess.
yeah, green.
Size do dynamite.
Well, you just want to buy new equipment. That's what happened to you. Please don't do it. Now, sometimes they may work, but usually when you start seeing batteries rusting or they are corroding with that little green out, that green film, that means the battery is old and starting to leak. And once it starts to leak, that means it's no longer useful. And the problem with that, yeah,
Mas I don't remember how long time they say feel you wait at the battery that got tell how much charge that much that
yes,
true?
that is actually true, right? Because what happens, the material now, that depends, that takes a practice hand. Like some people could go down the road and put enough tomato in a bag and feel it and know the weight. Just like somebody can lift a battery, right? And realize, this feel kind of heavy. You all ever realize a gas tank is much, much heavier than an empty gas tank?
Mas
Yeah. And it's full of gas. But look how much heavier it is, to the point where it's heavy. You can take an empty gas tank and lift it and heft it all over with one hand. Not really a full gas tank so much, nor do I advise you all heft it all over with a heavy gas tank. All right, so the same thing here. As the manganese dioxide starts to react with the zinc and whatnot, it's going to lose some of those properties. It turns into another material that is lighter, right? And by using it, that battery will actually get lighter as it gets a little older. But that's usually when you use a lot of batteries and you're really, really versed in using batteries, so you know the difference in mass. So you can pick it up and realize, yeah, this one feels lighter than the next one, right? That is actually true. So let's finish up. Once a leak has formed due to corrosion of the outer steel shell, potassium hydroxide, which is a chemical inside of it, absorbs carbon dioxide from the air to form a feathery crystalline structure of potassium carbonate that grows and spreads out from the battery over time. You all ever notice a white crusty substance on an old battery?
Yeah, Miss Karina.
That is the next type of corrosion, right? So when that happens, your battery is dead as can be. Don't even try to put it into your circuit. Try to put it into your components. All right, so reading, following along metal cathodes to the circuit boards where it commences oxidation, right? It can lead to permanent circuitry damage. So what happens when you put a dead battery or a corroded battery, or your battery dies while in a circuit, it is guaranteed to destroy your entire circuit because that corrosion spreads throughout the metal very quickly. So anytime you all take out a dead battery from something, you kind of almost guarantee that your apparatus has died. Right? That saddens me, especially for our multimeter testers upstairs in physics department. Anytime I see a corroded battery, I know that it is dead, because it probably would have leaked and formed the chemical reaction in the circuit and destroyed the circuit far before I would have seen it, which is what I'm kind of worried about right now with all my circuits in school. So when I go in school on Thursday, I'm going to go and take out all my batteries. Hopefully they're okay. Hopefully. Right. So what was that whole section there was for? You had to learn, number one, what the structure of your battery was, how it created electricity, and why leaks form. All right, so going on, we have internal resistance. The very nature of a dry cell introduces a small resistance in a circuit. All right, remember what is resistance? It's the opposition to the free flow of electrons. Just by making the materials that we use to make our battery has a little bit of resistance in it. Depending on the nature of the circuit, this resistance can be considered. Now, when we have a circuit where our total resistance is like less than 20 ohms, that little internal resistance is going to make a difference. All right, just to skip ahead, internal resistance is usually between 0.2 to 0.5 ohms. So when you're working with less than 20 ohms, that 0.5 is going to make a difference. Think about it. If you have $20 to spend and you're missing a 50 cents, that can make a little difference down your road, you know. Who is it? If you have like $10 to spend and you're missing a 50 cents, yeah, that will make a difference. All right, it's considerable in your scheme of things. Or we can disregard the internal resistance when our total resistance is more than 100 ohms. Think about this. If I have more than $100, not having 20 to 50 cents is unlikely to affect us too much, right? You don't ever see something with a cost of $100.20. I hope not. That's real. That real mean, boy. All right, so we consider internal resistance when we're working with a small resistance circuit, and we disregard it when we're working with a relatively higher resistance circuit. That's a little bit of sense, you guys?
Good.
Yeah. All right. It's just, you know, by comparing stuff one to the next. So let's read through. When considering currents, and voltages in a circuit, we must be able to distinguish some terms. So let's look at the terms we have to look at. We have EMF, which stands for electromotive force. This is the voltage that the dry cell produces itself. All right, so we have the dry cell itself, as the battery itself produces a certain amount of energy, and that is the electromotive force. That is how much it can the most amount of electricity or voltage it can produce. Voltage, the potential difference between 2 points in a circuit. The total voltage in a circuit is less than the EMF because the dry cell loses some energy in overcoming internal resistance. So if we have our where I've lost my pen. Okay. All right. My EMF is usually indicated with an E. My voltage is usually indicated with a capital V, and E is always greater than V. Why is E always greater than V? Because E is the pure power from your circuit, pure voltage from your battery, but the instant it leaves the battery, it starts to lose a little bit of energy. And we look at the voltage in your circuit. So there's a slight difference. We're going to see how to determine the difference just now. And then we have internal resistance. This is a small resistance associated with the dry cell. In circuits that consider internal resistance, it will label it as common R, and this is usually between 0.2 to 0.5 ohms. So if our circuit is a small resistance circuit, this little bit of resistance is going to make a difference. But if we have a high power circuit where we're using 100 or 1,000 ohms, that 0.5 is not going to matter. It's so small, it's not going to make much difference. So let's take a look at our gesso. It disappeared. All right, so let's look at our circuit. So generally, this is what our circuit looks like. This is what we've been doing so far. We have the voltage. Put that in a darker pen. All right, we have our voltage that is usually some value, 12 volts or something. We'll have our current coming out of our positive pole. We'll have our resistor of some resistance. We usually either have to find that resistance or it's given to us. And then we have our components connected to it. We always have an ammeter of some form in your circuit, and then we will have your, why is the pen writing so weird? And then we'll have our voltmeter. We're going to look at these two at the end of this handout. All right, so this is what our circuits normally look like when we're not considering all sorts of different parts. But if we take into consideration our internal resistance, this is what we write our circuit as now. You're going to see these in questions if you haven't seen it already. Instead of writing the dry cell with a V, we're going to have the entire dry cell represented as the EMF of the dry cell, which is your electromotive force, and the internal resistance of the dry cell connected to it. Now, we do consider this value, right, in some questions. So what we do, this little dotted line here represents the entire dry cell, right? So your entire dry cell is represented here. And what we do, we have the dotted line means this is what the cell is. But inside of that cell, we have our EMF value. So we always label the EMF value inside of your dry cell. And we are going to have our internal resistance inside of our dry cell. So this dotted line here represents our full battery. All right, so this is where we have to take values into consideration and whatnot. Now, how do we know the difference between E? All right, we just looked at E. And how do we know the difference between V? We have to consider internal resistance in our equation as V is equal to IR. We have V is equal to IR, that is voltage is equal to current by resistance. So we have been doing before, voltage is equal to your current by your total resistance. That is normal questions when we don't have internal resistance to consider. But the instant they put this little R in your circuit, we have to consider our internal resistance. So how do we do that? Your E, which is your EMF, is going to be equal to your V, which is the voltage in your circuit. This is the voltage that comes out of the circuit, that comes out of the battery. And then we're going to look at the voltage in the battery itself, because as the current comes out of the battery, we have to consider that that battery is producing a current I, and it has a little resistance. So here, if you want to write it down in notes, right, E is equal to your EMF, which is the electromotive force, is equal to your V of your circuit plus the V of your dry cell. And how do you work this out? Remember, V is equal to IR. So you're going to get V of your circuit plus the V of your dry cell is going to be the current produced by your circuit, produced by your battery, my apologies, and R being your internal resistance. So this is what our equation now becomes when we have to consider internal resistance. So you're going to have E is equal to V, this is the V that we use in the circuit, plus I by R. Please note we only use this equation when we take internal resistance into consideration. So if you want to manipulate this equation a little bit, excuse me, all we have to do is to carry the IR on the next side so you can get the voltage. If you want to work out what is the voltage produced in your circuit, it's going to be the EMF minus the little voltage of the battery itself, right? Which is the current running through the resistance of the battery itself. All right, so this is something, please note your two equations. One is the result of the other. Any questions yet, guys? No questions? Okay. Have you all done internal resistances yet in electronics?
No, miss.
Okay, all right. So we have to look at ammeters and, sorry. All right, ammeters and voltmeters. Now, what I do suggest you all do is to read up more on these if you wanted to, all right? Because we do have a millivoltmeter, and we do have a, not really millivoltmeters, we'll get milliammeters and microammeters to use in your circuits, but we're gonna read up on those a little later on. So voltmeter is an instrument used for measuring electric potential difference between 2 points in a circuit. It is always connected in parallel. So guys, when we have to start setting up circuits next term, you always set up your voltmeter in parallel. We're going to look at what parallel circuit setup is. Voltmeters are always in parallel. It usually has a very high resistance, usually anywhere from 10,000 to 200,000 ohms, so that it takes negligible current from the circuit. All right, so let's see here in our diagram. I should have put two diagrams. Let me copy and paste. Let's get our next diagram. One for the ammeter and one for the voltmeter. So when I have my voltmeter, what happens, because the resistance here is so high, a high resistance, what happens when I have my current here breaking up, I'm going to get I1 going into one side and then I2 going into the other side. That's correct?
Yeah, miss.
Yeah, good. Now, because the resistance here, because R is so large, that means I2 is going to be small. It's going to be so small that when you multiply the V equals the I by R, you are going to get the nearly pure V value. So let's just look at it. If we have just an example, suppose I have the voltage in my circuit is equal to 10 volts. My resistor of my voltmeter is 20,000 ohms. My current that I'm going to pull is really small. It's so small that I will get nearly all the current here passing through the resistor. So let's see. V over R, so you're going to get 10 over 20,000. So you could already see you get a really small number here. Right, 5 by 10 to the minus 4 amps. So the amount of current that is passing through this section of your circuit is so small, right? That means it's going to give us a very accurate reading of the voltage passing through this entire part of the circuit. All right, so this part of the circuit here, we want to get a really nice reading of the voltage because we are getting a really accurate value of the voltage in your parallel section. So this is what happens. It has a very high resistance, so that means it pulls a very small current. That current is so small that I is nearly equal to I1. We get nearly the full amount of current passing through your resistor, and that way we could work out the V is equal to IR. If you're a little confused, don't worry. This is why I'm telling you, this is why it works that way. We want almost all the current to pass through your resistor that we are checking. And that is how we can get our proper V is equal to IR. So that is for your voltmeter. And let's look at the ammeter now. An ammeter is a measuring device used to measure the current in a circuit. Electrical circuits are measured in amps, hence the name. An ammeter is usually connected in series. So note your difference. It is always connected in series, right, with your component. Whatever you are testing, it is in series, meaning they form the same line, right? A series component looks like this. It's on the same line versus parallel component. You have to form a junction where your current will break up. You all can see where we have a junction here and your current breaks up. But when we have series is when it forms one straight line. So the same amount of current is passing through your components. So an ammeter is usually connected in series with a circuit in which the current is to be measured. An ideal ammeter has a very low resistance. It's so low it can't be considered to be zero. So it usually has a resistance of like say 0.01 ohms, 0.00 ohms. Guys, if we had $0.01, would we say we had any money or nearly zero money?
Miss, that'll be a cent.
That's a cent. That's having any money to talk about.
No.
And if devalued our 1 cent.
Yeah, miss. I know
So-
good to see that.
So a 1 cent is not even worth anything. So this is why we said, say, when we have a very, very low resistance, it's going to be considered to be zero. And in this case, a 1 cent is zero. All right. So let's look and see how that works in the circuit. Now we're just going to look at how our ammeter and currents work. So if my R is so small, it is nearly 0 ohms, what is going to happen as my current passes through my ammeter, right? The voltage across here is going to be the same amount as the circuit. So that way you're going to read, going to get an accurate reading about the amount of current in your circuit. With the resistance being so small, all your electrons are going to flow very nicely and easily through your ammeter, and your device is going to be able to read what is the value of your current. So just remember, your resistance of your ammeter is very small. One is the opposite of the other. If you remember one, you should remember the next, right? The resistance of an ammeter is very, 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 very small. So it allows all the current in the circuit to pass through it, so that way we can read the current in your circuit. And for a voltmeter, we have a very, very high resistance. And by having that very high resistance, we are able to read the voltage in our component. Your voltmeter is always in parallel, and the resistance is very high, which is the complete opposite to your ammeter, where our resistance is nearly 0, and we connect it in series. So those are two things to remember when you all have to do series setup and circuit setup. Your voltmeter is always in parallel. Your ammeter is always in series. Always remember that, guys. All right, so moving on, power in a device. And this is going to wrap us up for the day. So the power used in or by a device is easily determined and measured. In fact, all appliances will have their power rating recorded somewhere on its housing, not someone. Somewhere on its housing. And how do we work out power? Power is equal to IV. This is your first equation about power. We did this earlier clock when we were doing electrical component, electrical quantities. So power is current by voltage. But by using V is equal to IR, we can get two other variations of it. So let's take this step by step. If I know I want to work out my second equation and my third equation, let's see how we can get it. You by no means asked to know this, but I'm just going to show you how they get it. So if I have V is equal to IR and power is equal to I by V, what I can do, I could go and take this entire V is equal to IR and substitute it for V. So I'm going to have I by, instead of the V, I'm going to put IR, IR. And I by I is I squared R. So that's my first variation. That makes sense, guys? All right, that should have been simple enough. And then the second one, if you want to get the second one, I can go ahead and use, instead of V is equal to IR, I could go and use I is equal to V over R, and using my equation of power is equal to IV, I can go and plug in one term for the next. So instead of the I can use the V over R. All right, so instead of the I'm going to use V over R in its place. So I'm going to get V over R by V. And V by V is V squared over R. So that's how we get our two variations. if you want to know how we get those two variations, and not by pulling in new values, all we did was just manipulate our equations. So continue reading. The unit of power is watts with a capital W. And it is common to see power ratings at kilowatts, which is thousands of watts. Kilo means 1,000, if you all remember your prefixes. So example, we're going to see things like 3,000 kilowatts, 10,000 kilowatts, right? And 3,000 kilowatts will be 3,000 watts. 10K will be 10,000 watts. So the K here represents 1,000. So it's just multiplying any number you see by 1,000. When we have to pay for electricity, we usually pay for every kilowatt used in an hour, or the amount of energy we use. All right, so what we use, we pay for electricity using a standard of kilowatt hours. If you all have never seen this, I advise that you all go right now after class and check your parents' TNTech bill, and you're going to see that they are rated in kilowatt hours. So we pay for energy, right? We pay for the electricity by using, look at how many kilowatts we use in every hour, and then you just multiply it across. All right, so here we have power is energy over time. So this is a new equation to learn. Now we're going to learn this equation again when we're doing electricity and when we have to do atomic physics. So don't worry too much about it. All right, so power is equal to energy over time, or P is equal to E over T. And if we cross multiply this, so if power is equal to energy over time, and we cross multiply them, you're going to get E. Remember, every number is assumed to have a 1 over it. So you're going to have E is equal to P by T, which will give you PT. All right, so energy is equal to power by time. So we can work out how much energy we use per month by looking at a conversion. All right, we're going to do this conversion tomorrow because we're nearly finished and we just did a lot. All right, so to calculate these, we use the conversion of 1 kilowatt hour. And 1 kilowatt hour is 1,000 because 1 kilowatt is 1,000 watts over 1 hour. Or if we want to use it, sometimes we're going to look at how much electricity we use in minutes. We convert the hours to minutes, so we can get 1,000 watts in 60 minutes. Or if you want to look in every second how much energy something is providing, right, which is what we do in physics. We tend to look at time in seconds. So when we're doing our questions, we're going to get them in seconds. So you're going to have 1,000 watts, and 60 minutes is equal to 3,600 seconds. All right, how are you going to do that? Remember, 60 minutes is equal to 60 minutes by 60 seconds. And 60 by 60 is 36. Add your 2 zeros, 3,600. So that's it for today. So you all, I am putting up this exact handout as it is in the group, so you all can follow it with the written notes. But we do have the class recorded, so you all can watch it back. It's for English, rewatch it, right, and make your final notes. So let's get out of the recording.